Let's look at a second example of diffraction. Monochromatic beam of light passed through two slits, forms an interference pattern on the screen. Distance between the slits 0.0550 centimeters. Distance to the screen 5 meters. Distance from central maximum to fourth maxima 2.38 centimeters. Determine the wavelength of light, then identify what color it is. First thing we got to do is sort out our numbers and figure out what they represent. D stands for the distance between the slits. We need to convert these all to meters. So it's 0.0550 times 10 to the negative 2 meters. L represents the distance to the screen. That's 5.00 meters. X represents the distance between the bright spots. This is 2.38 times 10 to the negative 2 meters. And N represents whatever maxima you're dealing with. Since it's the fourth maximum, N equals 4. We're looking for wavelength. Use the formula wavelength equals dx over NL. Put our numbers in. Be careful to put everything into meters. D 0.0550 times 10 to the negative 2 meters. X 2.38 times 10 to the negative 2 meters. N 4L 5.00 meters. Remember, when you're punching this in, you need to bracket the denominator. So it'll be 0.0550 to the exponent negative 2 times 2.38 to the exponent negative 2. Take that answer, divide it by basically 20, and you get 6.545. I guess we go to 3 significant digits, so it should be 6.55 times 10 to the negative 7 meters, or 655 nanometers. What color does that correspond to? Well, since that's one of the larger wavelengths in the visible spectrum, I would say it's red. Violet is the smaller wavelength. That's about 4 times 10 to the negative 7. Red or orange, you can make the justification, goes up to 7 times 10 to the negative 7. Be very careful what number represents what. That's the only time you'll really struggle with this formula, is if you mix up your variables.